Let's give a quick illustration of finding a solution to a system of three equations, three unknowns. As you know, any system of linear equations has only three possible outcomes. Either there is no solution to the system, or there is exactly one solution to the system, or there are infinitely many solutions to the system. When we look at this system in blue with equations 1, 2, and 3, at first we're not sure how we could tell which is the case. But a system of linear equations that's equal to 0 in each equation, we'll call that soon a homogeneous system. If you think about it for a second, well, it certainly has to have one solution. And that is, if x, y, and z are all 0, then all three of these equations will be satisfied. So it's certain that there's one solution to this system. Now let's solve it by combining the equations legally and see if there's more than one solution. So we're going to do this without matrices here in the first section. I'm just using this notation to guide myself through what I'm doing to each equation in the system. For example, the first equation, I'm not going to adjust. But the second equation, I will adjust by taking negative 2 times the first equation and adding it to the second equation. That's negative 2 times 5x plus 10x, 0 x's. Negative 2 times 5y plus 5y, that's negative 5y's. Negative 2 times negative z is 2z plus 2z is 4z. So these are the instructions for changing the second equation. Likewise, the instructions for changing the third equation. I'm going to take negative 1 times the first equation plus the third equation. That gives me no x's, 10 y's, and negative 8 z's. On the right-hand side, the adjustments still leave 0, 0, and 0. I'm going to keep adjusting. I notice now that the new second and third equations are actually multiples of each other. If I take negative 2 times the second equation, I will get an exact copy of the third equation. So 2 times the second equation plus the third equation will result in 0 on the left-hand side and 0 on the right-hand side. You know, that's a signal that I'm going to have infinitely many solutions. Because I have more variables than equations, and I certainly have one solution. Two of these variables are going to depend on the third. I keep cleaning up by noticing that the second equation now plus the first equation will eliminate the presence of y in the first equation. So here, 1 times the second equation plus the first equation, that'll be the new first equation, is 5x plus 3z equals 0. Negative 5y plus 4z equals 0. I leave that as it was. And 0 equals 0. It's certainly an equation. I'm not going to use it to determine anything, but I know that that's unchanged. Well, when I look at this box down here, these three equations, three unknowns, I see that x and y can be described in terms of z. I can divide the first equation by 5 and the second equation by minus 5. So 1/5 times the first equation, that'll become the new first equation. Minus 1/5 times the second equation, that'll become the new second equation. That makes x and y clearly dependent on z, clearly and directly dependent on z, and I can solve that x is minus 3/5 z, y is 4/5 z, and z is not described in the language of linear algebra. We call z free. It's free to be any value we choose. More vocabulary, the x and y, some people call bound because the x values and the y values are bound to the z value. One way to express this is to say z can be any real number, but x and y are determined by that value of z. So you could pick out many solutions. If z was 5, you'd see that y would be equal to 4 and x would be minus 3. If z is negative 15, then you'd see that y would be negative 12 and x would be positive 9. So for every value that I choose for z, I can find values of x and y. Together, all three of the values make the system equal to 0, 0, and 0. So this system has infinitely many solutions, and I've demonstrated how to describe them.